Materials Engineering and Nanotechnology from Politecnico di Milano in Italy, and also Bachelor's in Engineering in Mechatronics from Manipal Institute of Technology, India in 2012. She specializes in optical spectroscopy for identification and determination of biomarkers, predominantly related to cardiovascular diseases. She has used aquaphotomics extensively in her research for both in vitro and in vivo detection of lactate, lactic acid in blood. Now, I have been informed by the organizers that the presentation was pre-recorded and we will be showed us here. Is that right?
Hi, I am here, but I have also sent a video. I think it's better the video is going to play, and if there's any questions that I can answer in the chat.
Okay, please, the floor is yours.
Yeah, thank you. Hello, everybody. A very warm good afternoon and a very warm good morning from London. I am here to talk about our work, near-infrared and aquaphotomic analysis of water absorption in lactate-containing media. First of all, who am I and who are we? I am Nystha Baishya, and I recently graduated from University of London doing my PhD at the Research Center for Biomedical Engineering. Now, under the supervision of Professor Panicos Kyriakou, who also happens to be the director of our research center. Now, our research center deals with PPG research, basic and applied, optical sensors, wearables, spectroscopy, signal processing, etc. It comprises of academics, collaborators, postdoctoral fellows, and PhD researchers. Now, coming back to our work, first of all, the introduction. Well, I'm going to talk a little bit about the motivation of this project, near-infrared spectroscopy in lactate detection, aquaphotomics, of course, spectroscopy, spectral analysis, some of the results and a few conclusions. Now the motivation of this study. If we look at the world map where sepsis has affected, sepsis is responsible for the deaths of 11 million people annually. And there has been a clear correlation between COVID-19 and sepsis, because of which we are having to share a screen and not a coffee in Japan, which I'm really sad about. But the sad part is there is no gold standard diagnostic tests for sepsis. However, there has been some awarenesses and campaigns across the globe, and Surviving Sepsis campaign is one such campaign. And in their guidelines, they have mentioned that lactate can be a very important hemodynamic marker for clinicians to study the onset of sepsis. Now, how is this lactate predicted nowadays is the question. It is calculated or measured using invasive techniques. And that is where we wanted to say that near-infrared spectroscopy could be a very important tool or a sensor, maybe hopefully someday, for lactate continuous bedside monitoring of lactate. However, the challenges of near-infrared spectroscopy came as the water-related overtones or combination bands in the 1450 and 1940 nanometer wavelength, because of which direct quantification of other analytes in this region becomes impossible. And I would say lactate is one of them. So the peaks of lactate are so tiny that water absorption in this region completely overshadows lactate. So it came as a blessing when we found out about aquaphotomics, which was introduced by Professor Senkova in Japan. Through indirect quantification of through this indirect quantification of other analytes was possible. And that is where we wanted to see if we could use the same principles of aquaphotomics for lactate concentration determination. And for which we kind of made 37 samples of lactate in PBS for a set. And for the next set, we made 41 samples of lactate in whole blood. Now, all the samples were, the concentrations were verified using a blood gas analyzer, which is the gold standard in lactate determination these days in critical care patients. Now, once we had those samples, spectra of those samples were collected using, for the first batch was collected using the spectrophotometer from PerkinElmer, which is the Lambda, with some basic settings. And for the blood samples, it was the same spectrometer, but we introduced a detector, an in-gas integrating sphere detector, because we realized that blood has so many components inside it, and to get a homogenized scattering of all the components so that it's measurable and comparable with the PBS samples, we had to make this change. Now, once we had all the spectra, this is how the raw spectra look like in the top of the slide, as you can see, from 1200 to 1600 for both the data sets. There were not visible differences in the spectra because the concentration of lactate were kept very tiny, because we wanted to compare the concentrations to critical care. And that's why we had to do some pre-processing techniques like spectral difference, multiplicative scatter corrections, and Savitzky-Golay derivation. And after this, both the sets of the spectra look like what you can see at the bottom. Now, once we had these, we were ready for our aquaphotomic analysis. Now, we constructed aquagrams using the 12 water matrix coordinates, or WMAX, which have been already identified. So we did not identify new ones. Now, in the aquagrams, which I'll be showing in the next slide, and how we represent those, how we study those aquagrams is if the lower WMAX are activated, it reflects more free OH bonds. However, if the higher WMAX, for example, on the higher side, like 1488 or 1512, on that range are activated, which means that there are more bonded water molecules. Now, this is how the aquagrams look like. For the top one shows for PBS samples, and the lower one shows lactate in whole blood samples. Now, as it's very clear from both that from the above top, we can see that the lower WMAX were activated, which means that there were fewer lactate water molecular interactions and fewer or weaker hydrogen bonds, which means that the concentration of the analyte has an effect on these kind of solutions and can be determined from these solutions. However, from the whole blood samples, we see that the higher WMAX were also activated. For example, 1506 to 1516. And this shows that there were more lactate water molecular clusters, and we believe it was mostly because of the 4 hydrogen bonds. And in order to prove this, we further took our study by doing a multivariate analysis by partial least squares, in which we tried to predict the concentration of lactate using models that were derived and that were written, and the algorithms were written in-house. We found out that for the PBS samples, the coefficient of determination, or R-square, was 0.80, which was kind of expected because, as we said, that analyte concentration would have an effect on those samples because of fewer hydrogen or OH bonds. However, for the whole blood samples, the R-square was exactly opposite, and it was 0.28, which showed that it had more clusters of lactate OH bonds, and concentration of these, concentration of lactate from these solutions are very difficult to determine. Now, in conclusion, we can say that for the first time, the first overtone of water in the NIR region was investigated using aquaphotomics principles. This could be used to estimate concentration of lactate indirectly from the overtones of water, and also to separate the presence of lactate in different media, like we saw, that the PBS was completely different from the whole blood. In vivo studies using NIR and aquaphotomic principles will give an in-depth understanding of depth of penetration of light in tissues and blood. For example, in tissues, it is more evident that the lactate would be in a more bonded form. However, in whole blood, which is in the blood vessels under the superficial layers, we would find lactate in more free form because of less OH lactate molecular bonding. And we would understand where the signals are actually coming from. Results from this study will inform further research and development, leading towards a non-invasive lactate sensing technology based on NIR for use in critical care patients. With this hope, I conclude this presentation. Thank you so much. Do we have any questions? I am around to answer them. Thank you so much for having me.
Thank you, Dr. Baishya, for your nice presentation. I may ask the audience, are there any questions? Okay, then I will just ask about one thing. So 71 smoothing points. This is quite a strong smoothing. So did you check? I mean, first I would like to ask if this was really necessary, and if you tried also different pre-treatments. Okay. Mm-hmm.
Thank you so much for your question. Yes, we had tried a variety of smoothing points from 7 till 101 and 151 actually. And we believe that because the range of the spectra that we collected was really big, from 800 to 2500. So it was not only, the noise was not only because of instrument error that we always have, but I believe it was also the length of the spectra. And that's why when we did 71, I think we got the best results for our studies.
Okay. You didn't mention the resolution and the number of scans. Did you consider lowering resolution and increasing the number of scans to eliminate the noise?
Actually, yes, we did. So the lambda is not an FTIR, so it's like it's not an FTNIR, so it's a dispersive instrument. So the number of scans we did was 3, and it kind of we kind of increased the resolution to the maximum because that's the best we could get out of these spectra. So it was clean and clear, the spectra, but however, we also had small tiny disturbances in the spectrum. Actually, and I think, sorry.
No. Sorry, I didn't want to interrupt. Maybe I'm a bit rushing because of the time, but I just wanted to mention that actually you should try, especially for dispersive instrument, actually lowering the resolution if you have the problem with the noise.
May I comment on this?
Yeah, sure.
Sorry. So there is a really wonderful paper that she published recently, specifically on comparison of instruments in detection in this for this purpose. And as a person who had also the same instrument, I know what are the problems with different instruments, let's say. So, but she has a really wonderful paper. And I have one question. The path length of your cell was how long?
It was 1 millimeter. 1
millimeter. You can try with 0.5. You will have perfect.
Yes.
But thank you. You're very welcome. Thank you.
Thank you. Do we have any more questions?
I have a comment only. When you do prediction, you make a model. And if you make a model for individual patients, then your model will work beautifully. Yes. When you make a model based on all patients and try to predict an absolutely new patient, then it will be very difficult. And then you get this 0.28. So yes. There is a certain, but we have written papers on diagnosis, so there is a way and to overcome this. Making you can it's all about how you treat the data, analyze the data, and make the model. So thank you very much. It's a very interesting topic.
Thank you so much. We look forward for collaboration so that we can have more papers in diagnosis. Thank you. Thank you, Jelena.
Thank you, Nystha. I can't wait.
Thank you.
Okay. Are there any other questions? Okay, then in such case, thank you once again, Nystha, for your exciting talk. I wish you much successes in this direction. This seems very, very promising. And unfortunately, we have come to an end. So I would like to thank all the speakers and participants. It was a true pleasure to hear all your exciting talks. Thank you to all the participants for the questions and discussions. And thank you for the organization of this conference. Much congratulations to Professor Tsenkova. Thank you, Jelena, for helping with the organization. And now I need to close the session. So once again, thank you all and hope to meet you again soon. Thank you.
Thank you for sharing.
Thank you, Steve. So now, after this wonderful session, we are left with a little time, but it is time we are going to start immediately with the General Assembly of Aquaphotomic Society. So please stay with us before the poster session, and I will now immediately give word to Professor Tsenkova.
Thank you very much, Jelena. Having assembly at this international conference is our second time.